What I'll do is I'll quickly go over something that we've already done before, but re-emphasize because depletion region analysis, as I said, you will encounter at various places in Schottky barriers, PN junction, bipolar, MOS, everywhere you'll encounter calculations of depletion region. And what we have been saying is that do not, I mean, you can do it through the root of equations, but a better and more intuitive way is to do it through graphical analysis. Okay, so let me go over quickly so that everybody understands all the features of this particular part here. So as usual, for example, for a PN junction, we know that there is depletion charge here and there's depletion charge here. We know the charges here and here, Q and D and minus Q and A up to Xn here and up to minus Xp, right? After that, we said what we are going to do is, what is the first step? We sketch the electric field, right? So that's what we do. We start with F. That's the symbol that we're using for electric field, and we sketch the electric field. And while sketching the electric field, what do we have to remember? Two things. One is outside the depletion region, field is zero, right? Outside here and here is zero. The other one is, what we have to remember is, what is the Poisson's equation in terms of field? Del F by del X here, if I'm looking at this region, Poisson equation is Q and D by ES here. So that gives us the slope, right? That gives us the slope of the field here. And so field starts from zero here and slope is positive. So it has to go down here. It can't go up because that would imply a negative slope, right? So it has to go down, and that's where we end getting this particular segment. When we come to this particular region here, Poisson equation becomes minus Q and A because charge is negative, minus Q and A by epsilon s, the slope is negative now. And the slope, because field is continuous, so it must start from here and then go to eventually zero here, right? So we are arrived at the field plot. Once we get the field plot, then what we have to do is we can calculate, for example, what is the maximum field. If this is zero here, the maximum field here would be Q and D by ES, the slope here, multiplied by the extent of this particular region, which is Xn here. So we know the maximum field in terms of Xn here. Then the next thing that you do is you take the area under the curve, and that gives you the net voltage here. If it's in equilibrium, the net voltage across the junction is VBI, and VBI will be equal to half this value here, Emax, or maximum value of the field, Q and D Xn by ES here, multiplied by the total here, Xn plus Xp, right? So this will give you now, we know the relationship between Xp and Xn, so it will give you Xn, and then you get the total depletion width, and you get the maximum field, and you get everything that you want from analysis of depletion region here, right? So these are the steps here. You sketch the field and you remember the Poisson's equation. All right, we had seen this particular example in the last class, right? So metal, and then there is an intrinsic region, and then we have an N-type region here, and obviously the depletion width will lie somewhere here. And so we said again sketch the field here. We can obviously find out VBI and all that here because the depletion width lies here. So VBI we can find out. So again sketch the field here, and because it's intrinsic, and we assume that the charges here are negligible. Any electrons and holes, mobile carriers in a depletion approximation are neglected. So mobile carriers are not there. There's no background doping. So del F by del X is zero here. So that gives us a constant part here, right? Constant part here. In this region is a normal N-type region. So del F by del X is Q and D by ES. So it's going to go like this, right? So that's how we sketch the field for this system here. Metal, intrinsic silicon, and then N-type, right? And then of course if we assume it to be X naught here, then the field here, we know the slope becomes Q and D by ES X naught, same field everywhere here. And then we write down the area under the curve, which is VBI. And once we solve it, we'll get the extent of X naught, and therefore we can get the total depletion width and everything else that we want here, right? So it starts from sketching the field. And I region, note that I region is being modeled as I said, there's no NNP or negligible NNP, and there's no doping. So I region is always characterized by zero slope in the depletion approximation. So zero slope here, and then we get this here, right? This part is of course the area here. This part is the area of this particular part, and the total sum of the areas must be equal to VBI or VBI minus whatever voltage is applied, right? So that's the step here. This one I want to emphasize once more. So we know how to handle the intrinsic region. Intrinsic region is characterized by zero slope. How do we handle N plus? Okay, so this was a problem, metal, Nd, N-type doping, and then is followed by Nd. This is also N-type, but is heavily doped. Okay, so how do we handle this? Again, we sketch the field, and right, so we draw a line here characterized by this. We know the slope here, QND by ES here, so we know the slope here, so we sketch it here, and we know the slope here. Slope here is going to be very high, so I'm going to draw it like this here, very high. If the doping is given, we know what the slopes are, but very often you don't need the doping. The fact that it is N plus, you can do the analysis without knowing what the exact value of the doping is. It doesn't really matter. That's what I want to illustrate to you. So it's some high slope here, right? So we get a field plot which is like this here. The next thing is, if I call this F naught, this field at this particular point, the field at this particular point will be how much? F naught plus the slope multiplied by 0.2 micron here, right? F naught plus QND by ES into 0.2. So now we know the field is F naught here and this one here. Next, what is the next step now? Area under the curve is equal to built-in potential. Now note that what I've done is, in this case, built-in potential, area that you're seeing here is this big area that you see here. In addition, there is this small area here, right? And that's where I'm saying the drop here is negligible. When you encounter N plus, the drop in the N plus, the voltage drop in the N plus is usually negligible. All right, so I'm going to justify that for you. So what I've done is then I've assumed that this area is negligible, and then I'm only taking the area of this particular part here. And the area of this particular part is a trapezium here, half. Field here is F naught. Field here is F naught plus QND 0.2. So this is this particular term here, multiplied by 0.2. 0.2 is the total width of that particular region. Yes. So this one, this slope, is not necessary. That's what I'm trying to tell you. I'll prove it for you. Now you may be wondering, if you look at this particular one, you are neglecting the voltage drop here, but you're taking this field F naught. Where does it come from? This field F naught. What is the source of this field? The field here is 0. What is the source of the field? The N plus region itself. Right? The source of this field is whatever charge is there in the N plus. That's why it's increasing, right? So it seems, if you look at it, well, you are assuming that there is a field here, F naught, and this comes about because of charge here. But when it comes to voltage, so you're assuming that the field is there. But when it comes to voltage, you're saying that the voltage drop here is negligible. Okay, so that we need to justify that. All right, so I'll show it to you. So I'm assuming that the drop here is negligible, and we are doing this calculation, right? So that gives us VBI. Now, how do I justify? See, in semiconductors, what happens is there are two ways of approaching it. One is through some logical arguments, right? Logical arguments and all that you show, well, the voltage drop is negligible here, right? So through some arguments, you say that assumption is justified right in the beginning. And then you make the assumption and you do your calculation and fine. The other way is, if it's not very clear, sometimes you know that, well, I'm going to make this assumption, but what I do is I make the assumption, I do my calculation, and I come back and check whether my assumption is consistent with my results. Okay, so that's the strategy that I'm going to use. So I'm making an assumption that the voltage drop is negligible, right? And I'm doing the calculation now. I'm doing the calculation, and through the calculation, what do I get? F naught, right? Now I'll get F naught. Now once I get F naught, can I estimate the width of this particular region here? Let's say if I know the doping, say 10 per 19. Can I know the width of this particular region here? Can I calculate the drop here? All right, so let's do that. Let's take 10 power 16 here. Suppose I take phi b is 0.7. So what is likely to be the built-in voltage? Metal, 10 power 16 and N plus. The built-in voltage is likely to be? In N plus, where is the Fermi level likely to be? Almost coinciding with the conduction band, right? So that phi n is negligible, 0. So the built-in voltage is also 0.7. So I have 0.7 here, and I have all the other information that available to me, so I can estimate F naught. So if my calculations are correct, I will get an F naught of 1.95 into 10 power 4 volt per centimeter. That's the value of F naught that I'll get. Once I get F naught, let's calculate how much is this region here, right? How much is this region? How do I calculate this region? F naught, what is the slope in this region here? Q ND2 by ES, correct? ND2 is what? Doping in this region, right? In any N region, what is the slope of the field? Is Q ND by ES here. So that's the slope here. So what I'm doing is I'm assuming an N plus region of a doping of 10 power 19. So if I assume 10 to the power 19 here, I've calculated the field, and this value turns out to be 1.26 into 10 power minus 8. This region here. 1.26 into 10 power minus 8. How much? 1.26 angstrom. So it's very, very narrow, 1.26 angstrom. Under depletion approximation. You can always, go back and question whether in such a small region is depletion approximation valid or not, but I'm not bothering about that right now. So this is 1.26 into 10 power minus 8, right? So now, what did I assume? That the voltage drop here is negligible. How do I calculate the voltage drop? Voltage drop would be half, this is a small triangle, right? Half F naught multiplied by this 1.26 into, this 1.26 angstrom. That's the voltage drop. And if you do the calculation, how much does it come out to be? 0.12 millivolt. 0.12 millivolt. Right? So the voltage drop in this particular region, in these N plus regions, is very small. But field is not negligible. Why? Even though the voltage is very small, 0.12 millivolt here, but the width of this particular region is also very small. And the field is voltage divided by the length scale. And so the field is significant here. I can't assume F naught to be 0. F naught cannot be assumed to be 0. Right? So F naught is there because of the charge here. But the voltage drop in this particular region is negligible. 0.12. So wherever you see N plus, very small N plus, the voltage drop in that region is not going to be significant. The voltage drop will always be more across a lightly doped region. Much more likely. So here I'm talking about 10 to the power 16 here, and this is 10 power 19 here. We are talking about 3 orders of magnitude change in the doping level. That's where most of the voltage will drop, not here, N plus. So there's no need to, do this calculation, take area under the curve and all that. It's not required. Voltage drop here becomes negligible, N plus. But at the same time, the field is not negligible. So keep that in mind. Field is not negligible, but voltage drop is negligible for an N plus region. Okay. So let's go on to our problem number 3. This I said is a problem. I have metal here. In between I have a semiconductor. I've slightly changed the problem. I've made this, or maybe it's the same, 0.3 micron. I think it's the same, right? And minus 10 here and a ground here. And the barrier heights we've already given you. Metal, barrier heights here and barrier heights are 0.7. And with the barrier height, with the doping given, I can calculate what the built-in voltage of each metal semiconductor junction is, which is 0.55. Okay, so those are easy to calculate. And as I was saying, I want to find out what is really happening at minus 10 volt. How much is the depletion width? What are the fields and all that? I want to find out. I want to analyze this particular depletion region and find out what is happening at minus 10. So as usual, we said we'll sketch the field, right? And for the field, I was saying we have various options that are there. It could be that my fields are like this here. The slopes are, of course, going to be Q by ES ND. That's what the slope is going to be, Q by ES into ND. So it could be like this here. I don't know. I'm not looking at I don't know what will happen at minus 10, but it could be that I have a depletion region here associated with this junction, and I have a depletion region here associated with this junction, and the two depletion regions don't overlap. And there is a field which is, you can see here, there's a zero field, which means this is a neutral region. Or I could have a situation which is like this, where the two depletion regions just touch each other. I could be in that particular situation. At some voltage, you know that if I apply higher and higher voltage here, eventually depletion will extend, and they'll merge, just merge. And that is the situation here. Or I could have a situation, as I said, where this particular junction is sort of eating into this particular junction. Is taking its charge away. Because if let's say this one is at equilibrium, this particular one here, and it has this much charge associated with it. Now this particular junction is taking away charge from here. Or I could have a situation here. In this case, what happens? The field at this particular junction becomes 0, which means that this particular junction does not have any charge of its own. The entire charge here has been taken over by this junction here. And it could be further down as well. I could go and then maybe draw another line here. So the issue is at minus 10 volt, where am I? What is really happening? Okay. So you can go step by step. The first thing that you could do is, let's say I don't apply any voltage here, reverse bias. It's equilibrium. I have 0 here, I have 0 here, and I have 0 here. Let's estimate the depletion width here. Depletion width here and depletion width here, assuming that they don't touch. Okay. That's easy to do. One can easily calculate because I know VBI and I know the voltage drop across this junction. How much should it be? VBI, the voltage drop across this junction also should be built-in voltage VBI. So can I estimate how much is this depletion width? It should be straightforward. If this field is 0 here, the field will be Q by ES ND times whatever is the depletion width, and then area under the curve is equal to VBI. So all of you should be able to, without any problem, estimate. Let me give you the answers first, and then you and make sure that you can get the answer here. So area under this curve is VBI. So what I will find is that my depletion width at 0 bias is about 85 nanometer. Which means what? This region is 85 nanometer and this region is 85 nanometer. Both these solid lines that you see here, 85 nanometer. So at equilibrium, they're not touching. They're apart. 85 here and 85 here. So there's a neutral region. Okay. Now, suppose I ask the question, at what voltage will they just touch each other? Is that easy to answer? What am I saying now? What should be the depletion width associated with this junction now? If this is fixed, 85, so the other one should be 215. So depletion width associated with the first junction we are saying is 215. Now we know the depletion width. Can I calculate how much reverse bias I have to apply? Because area under the curve will be equal to what now? Reverse bias plus VBI. Right? So area under the curve will be reverse bias plus VBI, and that would be from here to here is this particular graph. Right? And I can calculate how much reverse bias I need to make the junctions touch each other. And suppose I do that, I will get minus 3 volt. I will get minus 3 volt. So if I apply minus 10 volt, where am I now? Definitely somewhere here. Junctions are already touching each other, and in fact, if it is minus 10 volt, my first junction is eating into my next junction here. It's taking away the charge from the next junction. So next, let's calculate this part here. What does this show? That the field at the other junction has fallen to 0. Now, what will area under the curve denote? Can I calculate how much voltage is needed to get this? The total depletion width associated with the first junction now is 0.3 micron, right? So the total depletion width associated with the first junction is 300 nanometer. What I need to do is calculate how much is VR. How much VR is needed to get into this situation. Let's say I find it's equal to minus 7 or whatever. I don't know the value. Okay, you will probably find it's less than minus 10. So it's under minus 10 here, whatever that value is. Now what will happen then? At minus 10, what will happen? The whole region is depleted. Alright. So at minus 10, what does the situation look like? How will the field look like at minus 10? Field cannot be 0 here. Where will the field go? Where will the field go? Does at minus 10 the picture look like this now? It will go down here further, and then so looks like more like this. The picture, huh? It is a capacitor, but not a real parallel plate capacitor because there are charges inside. Not a simple like that. So this is the picture then I arrive at. How did I arrive at -10? So I went step by step and I saw that the two, for the, that at zero bias, the depletion regions don't touch. For depletion regions to just touch, I need about -3 volt. To get into a situation where field falls to 0, I need something here. You need to calculate. And I'm just saying it's less than 10. And therefore at 10, this is the situation that is here. Now how do I proceed? I say the field here is, let's say, F0. The field here will become F0 plus QND by ES into 0.3. Correct? And what is the area under the curve? That's interesting. What is area under the curve? That's why don't make a mistake. Area under the curve is 10. Area under the curve is not 10.7. It's 10. It's 10. And then you solve this and you will get F0. I'll sketch it for you and show. You get F0 and then you get everything else. You get the field here, you get the field here, and you get all that.